All right, good morning, everyone. As you probably guessed, this is continuous delivery for architects. This is really the intersection of the engineering practices of continuous delivery with the role of architecture. And it turns out there are a lot of surprising amount of synergy between those two things, which I'm going to investigate as part of this talk. So I want to talk about three broad things in this talk. First, I want to talk about some related concepts around continuous delivery and architecture, including some engineering practices and some metrics and things like that. Then I'm going to talk about component-based development, both components, which are compile time dependencies, and services, which are runtime dependencies. This also touches on microservices, because that's just a specialized version of a service-based architecture. And then finally, how do you evolve from one kind of architecture to another, which seems a lot of people are doing these days. So let's first talk about some concepts in architecture. And the first one I need to talk about, of course, are some of the engineering practices in continuous delivery. From my perspective, continuous delivery really is just a convenient marketing umbrella term around efficient engineering practices for agile projects. And so continuous delivery has several parts. In fact, I'm doing an entire workshop on Friday about this subject. But a few of these things are particularly pertinent to architects. Now, one of them is this idea of a deployment pipeline. So in continuous delivery, you replace continuous integration with this idea of a deployment pipeline, which has multiple stages, and you try to achieve success through each of those stages, and you get more and more engineering sophistication in each one of those stages. And so as you look at a deployment pipeline, one of your first challenges as the architect is going to be exactly what stages do you have, because there's no prescribed set of stages that you are supposed to have before you're properly doing continuous delivery. So you may have, for example, a commit stage and a functional testing stage and then user acceptance and staging and on and on. Each of these joined by a kind of a scratch area where you can keep things, intermediate results of builds as you build up more and more sophistication. Over time, the goal here is that you want increased confidence in production readiness. So you'll go through a more and more sophisticated battery of tests and those sort of things as you go along. In this continuous delivery world, pipeline stages become feedback opportunities. If you're accustomed to working in an agile project now, you're accustomed to having continuous integration, and you started treating continuous integration kind of as a magic bucket where you can do a lot of stuff. So you build there and you run unit tests there, and maybe you do code coverage and other sorts of metrics and other things, and maybe you've got functional tests running and other things. What we're trying to encourage here is separate out that bucket of things, make them individual stages in a deployment pipeline, because that allows you to optimize the engineering practices around that stage and the audience for that stage, which is an important perspective. So you have to be the ones that set this up. But there's another responsibility that kind of comes along with this. There's a special stage in this deployment pipeline world where you start taking on additional responsibilities. In most of the continuous delivery literature, it's a user acceptance testing stage. That's just a coincidence of literature. You get to decide exactly when the stage is, but it's the stage in which you start really thinking about operationalizing what you're building. And so this is this idea of a deployment pipeline kind of spread out all together. The commit stage is what you normally think of as continuous integration. This is where your code is integrated and commit and unit tests and those sorts of things are run. This artifact repository is temporary storage on the file system to take intermediate artifacts that you've built and build up a bit more and more sophistication. But you'll notice a particular step here under this acceptance testing stage called configure environment. And you'll notice that once you start doing that, you do that on all these downstream stages. This is the place in the continuous delivery world where you start spinning up the ecosystem that your code's going to run on. Because the perspective in continuous delivery is, look, your overarching goal is to make deployments a lot more predictable and stable. So how do you do that in a world where it has lots of moving parts and people keep adding more moving parts to it? The way you do that is start treating software as an entire universe, an entire ecosystem. So it's not just your source code, your database schemas, it's also the operating system that it runs on and all the ancillary stuff that makes it work. So this configure environment stage, so let's say you're building a Java web-based application. This configure environment stage, you'll now take a Puppet or Chef script and start from a raw IP address, almost always on a virtual machine now, and say, okay, this code needs to ultimately run on CentOS version something with Apache and Tomcat and 47 jar files and these user groups and permissions set up. So you'll spin up a Puppet or Chef script to build that environment up. You'll then deploy your binaries onto that environment, make sure that environment's up and running, and then run your acceptance tests on it, or do manual testing, but you still do that same configure environment stage. Even if you're doing continuous deployment, you're still doing that as part of that production push. You don't have to do that in this world, but that's the same kind of idea in this world. Now, whether it's a Puppet or Chef script or whether it's some sort of Docker image or something like that, the idea is, and the point of this is, that as the architect in this world, you have to start thinking about how does this work in operations much, much sooner than you have to in other kinds of architectures, which was kind of a last thing. Maybe you thought about it a little bit at the first of the project, and then the last of the project as you're getting ready to go live, you have to start thinking about it. Now this becomes a daily concern of the architect is what does this look like running in a production-like environment, because you're going to be managing this as part of the build cycle, as part of this deployment pipeline. What we'd ultimately like to get to, most of the literature in the continuous delivery world kind of assumes monolithic architectures, but the other goal that we're really after in that continuous delivery world is by doing smaller and smaller increments of change. So one of the engineering principles in the continuous delivery world is try to do things as eagerly as possible rather than putting them off as long as possible. And things like service packs or any kind of change to a component in our system, we want to try to incorporate that change as eagerly as we possibly can, because that is exactly the time when you pay the least engineering cost to incorporate something. The longer you wait to incorporate something, you pay a higher cost in terms of pain of getting that to work, because now you're letting combinations of things build up, which is the really tricky, complex thing in software. So where we really want to get in this world is have a system set up so that when one of the components changes in your world, in a compilation-based world, when one of your components changes, it automatically triggers a build that ultimately builds in an integration pipeline, the application that you're building. And I'll talk about some of the challenges and other things with that in just a bit. Another kind of realization that this continuous delivery world, the way that this has changed the world of architecture, is it's starting to make us realize that yesterday's best practice is tomorrow's anti-pattern. We keep building architectures around constraints that exist, and then those constraints disappear, and the architecture with all those constraints built in exists for a long period of time. What this really points out is that the abstract job of software architect is sometimes at odds with the practicalities of the messy real world. Because one of the goals of software architect very often is to achieve maximum code reuse. Try to build single sources of truth for things so that you don't have duplications running around all over the place. From a logical standpoint, that makes perfect sense, because obviously duplication is bad. If you can unify things in a single place, that's a good design in an abstract way. But then you have to think about operationalizing this in a messy real world. Let me give you an example of where this ends up biting you. We have a client who runs an airline. And they, architects, had done as you would consider a best practice in the architecture world, built a customer service that encapsulates everything the organization knows about customers. It's all unified in one place. It's all backed by a clustered database that has the giant customer table and all of its ancillary join tables to it. So they've built a single source of truth for customer, which they're quite proud of. And then a volcano exploded in Iceland. And pretty much everyone who had tickets in this airline called their customer service desk to say, hey, is this volcano going off going to affect my airline ticket? Which means that people on the other side of the world couldn't board their airplane, because now the customer service is completely slammed, and it is now the single source of bottleneck. And because it is the only place you can go to get customer information, every part of the business is now affected. From a practical standpoint, this business would be much better off if they had two customer services, one that primarily dealt with boarding things and one that primarily dealt with customer service. And even if there was a little bit of duplication or, shocker of shockers, a little bit of conflicting information in those two things, it would still serve the business better than having the single source of truth that fell over at some point because you built an architectural bottleneck. You have to think about what is it going to take to operationalize this architecture. When you do whiteboard diagrams and draw boxes with lines on them, that's a useful exercise, but it's really only a snapshot. It's kind of a two-dimensional view of architecture, and architecture is really four-dimensional. So you have to take that two-dimensional view and then make it three-dimensional by making the boxes with actual labels. So you put ORM on the box on a whiteboard, you make it three-dimensional and say, okay, this is Hibernate version 4.3.1, and now you make it four-dimensional by saying, I know how we're going to safely upgrade that in 6 months to Hibernate 4.3 when it comes out. So you've got to think in more than just pictures. You've got to think about what does this look like when you make it real, and then what is it going to look like in 6 months when I need to keep it real. That's something that we do poorly in the architecture world. That's what leads to these kinds of architectures where you have lots of shared infrastructure and other things like that, which is really good from an abstract logical standpoint, but becomes troublesome when you think about operationalizing these things. Because over the last few decades, we've really fought a battle in software architecture to get better and better at scalability. And so we've built a lot of very interesting shared resource styles of architecture. The really common architectures that you see out in the world right now, like the traditional layered model view controller architecture, is very much a shared resources style of architecture because you're sharing all those things in those horizontal layers. That allows you to share resources and build application servers and things like that. But it also creates a lot of coupling between all those pieces within those layers. And what we started realizing is that just like yesterday's best practice becomes tomorrow's anti-pattern, shared resources, getting really efficient at sharing resources is less and less of a concern for us now. In fact, because Amazon will rent you resources for pennies on the dollar now, resources can be spun up almost at the drop of a hat. Now the problem we have is all the coupling we introduced trying to achieve shared resources. All this coupling at layers makes it very hard to do isolated changes. So I need to make changes to the way my customer behaves. If I'm in a traditional layered architecture, that means I'm sharing the customer persistence code with all the other orders and line items and catalog and all the other parts of my system. If I need to upgrade the capabilities of the customer, I can't just do that in isolation because it affects everyone in that layer. So they're all coupled together at that framework level, which makes upgrades and things like that difficult. It encourages big bang deployments because, well, we can't really change one thing, so let's change them all together and then we'll big bang it, but that leads to more and more pain, which we're trying to get away from. Makes things like upgrades difficult. What this does is it adds friction to change. And that's one of the things that we really are trying to enable in the continuous delivery world, is to make change something that you expect as part of a daily thing, that you want to be able to take changes that apply to your software or your ecosystem and apply them very aggressively to make sure they haven't broken some assumptions about the way your world works. While this makes sense from a logical standpoint, this is problematic from a deployment pipeline standpoint. It's hard to spin up a deployment pipeline with a thing like an enterprise service bus in it. This is really hard from a domain-driven design standpoint, and this makes things like evolutionary architecture more difficult. I'll talk about alternatives to this as I talk about service-based architectures in just a bit. Still toward this idea of building up some concepts or useful concepts for architects in this continuous delivery world, let me talk about a few metrics and monitoring tools that are useful in this world. These are tricky kinds of projects because this is essentially doing architecture on an agile project. And the metaphor here is that you start off, you take off from the ground in ultralight and you turn it into a 747 while you maintain airspeed and velocity the entire time. That's what you're trying to do as an architect. So that you have to have a couple of kinds of metrics at your disposal. So let me talk about some metrics and I'll talk about some tools and uses for them. Two incredibly useful code-based metrics for architects in this world are cyclomatic complexity and afferent-efferent coupling. So let me talk about these in turn. These are not new metrics by any stretch. Cyclomatic complexity has been around since the 70s, and this basically applies to any structured programming language. It gives you a numeric complexity value for a function or method in a code base, allowing you to make apples-to-apples comparisons between methods or functions to see which was more complex. Tom McCabe created this formula, and this is the formula, edges minus nodes plus 2, where nodes are lines of code and edges are possible pathways through code. So if you look at this little C-like method and sketch it out in this lines and edges view, you'll see that this is 4 minus 4 plus 2, so the cyclomatic complexity of this little method is 2. But it's boring when the numbers cancel each other out like that, so a slightly more complex method is this one. And you can sketch it out in this edges nodes view and count things up, 8 minus 7 plus 2. So the cyclomatic complexity of this method is 3. Excuse me, this is one more complex than the method we saw previously. Cyclomatic complexity is an interesting metric because you can use it and you can also use derived metrics. So one of my most fun tricks to do is when I encounter a brand new code base is go find the 5 most complex methods or functions in that code base and then ask myself a question, is this essential or is it accidental complexity? In other words, have I just discovered a really hard problem, or have I just discovered some really clever programmers who have made it really, really hard for no particular reason? My friend Glenn Vandenberg has a great quote that bad developers will move heaven and earth to do the wrong thing. The amount of innovation that bad developers put into completely horrible ideas is really stunning. If they could just apply that amount of innovation to good ideas, you might see something quite amazing. The other thing you can do with cyclomatic complexity is combine it with another of these metrics I'll talk about in a second and try to go find the most important thing in your code base. Well, let's talk about this other metric, and I'll talk about that one. So let's talk about afferent and efferent coupling. These are 2 coupling metrics which become important to architects. Afferent coupling are the number of incoming connections to a code artifact, and this can be a class, or it can be a package or a namespace. And the efferent coupling is the number of outgoing connections from this artifact. And the easy mnemonic here is that efferent starts with E, which is the same first letter as the word exit, so those are outgoing connections. One of my favorite tricks is to combine 2 metrics together, and so one of my best emergent design tricks is to get a tool that will produce both cyclomatic complexity and afferent coupling metrics for each class. What you find by combining those 2 things together and looking at the combined 2 numbers, you don't add them, but just look at the combined 2 numbers, are the most important complex things in your code base. And very often, if you're coming into a new code base, you want to see what are the most complex, important things that I need to understand in this code base. The combination of those 2 metrics, afferent coupling and cyclomatic complexity, will very often lead you there like a dividing rod. I've looked like a magician several times by walking into a client, quickly running a metrics tool and then saying, oh, I bet the biggest problem child you have in this code base is this group of classes, and they look at me like I've pulled a rabbit out of a hat, but I haven't. I've just applied a couple of metrics. So let's talk about uses for these metrics on projects. There are 2 typical uses for these kind of metrics. One is information radiators and the other is probes. Information radiators are things you wire into a build system so that you can get constant feedback on something, so that you can look at trends and things like that. Now I'll talk about a few of these. Most of these are very Java-centric because I spent a lot of my time in the Java space, but there are tools that exist in both spaces. And actually this first one is completely agnostic. This runs across a bunch of different platforms. And you can actually get these graphs from several different kinds of tools. This is a Kvyat graph, or sometimes called a spider graph. The idea behind these graphs is you set up acceptable ranges for metrics. So complexity here is our friend cyclomatic complexity. So you can say, okay, it's acceptable for me to have between 2 and 4 cyclomatic complexity, but my max I want to be below 8, between 2 and 8, and the number of methods per class, and the average depth is how much you've indented within a class, etc. And so you set up all these acceptable ranges, and then you graph actual classes onto the top of it. This is one of the classes from Struts graphed onto the top of this. And if this were a perfect class from a metric standpoint, it would fall exactly into the middle of the donut of goodness here. And the further it diverges from that nice donut shape, then the weirder this is from a metric standpoint, and so the more you should pay some attention to it. In fact, this one has an unusual kind of a boomerang shape, because you'll notice that the average complexity is below the threshold, but the max is way above the threshold, and it has a huge number of methods in it. This boomerang shape is actually quite common in Java code bases. Does anybody know why that is? Is anybody here a Java developer? Could figure out why this magic property exists a lot of times in Java? Nobody? Yep, exactly. Somebody said it. It's the way that Java works is they don't have a native syntax or property, so there's a convention in the language that a get and a set method yield a property. And so you get these value objects in Java land that are 20 fields and then 40 getters and setters, and then the language also mandates you create an equals and hash code method that accommodate every single field. And so the recipe for that is a whole bunch of little tiny methods, which gives you an average complexity below the threshold, and then a couple of gigantic, horrific methods, equals and hash code, that get you above the threshold. And of course, you end up with lots of methods per class, because each one of those properties is a pair of methods. And so this kind of boomerang shape is quite common in the Java world. So the point of that is some languages tend towards some shapes on these, and you have to watch out for that and don't just automatically think that all your things are broken, and you may end up adjusting your ranges, something like that, to accommodate that. My colleague Eric Dernenberg has created a bunch of really cool visualizations, and this is one of them. These are at his site. In fact, he's very slowly working on a book about visualizations in software. And this shows an example of a clever idea of how to visualize something that normally doesn't have a visual aspect. There's a tool in the Java world called CheckStyle, which is a static source checking tool. It's similar to FXCop in the .NET world, or some of the tools like RubyFoo in the Ruby and Rails world. What it does is go through in all these categories of violations. It complains about things. So it has categories like Boolean expression complexity and cyclomatic complexity when it's above a threshold, how many nested ifs you have. So it's a static source checker. But when it reports its results, it reports the numbers in each category, but it doesn't report any kind of cumulative results. And so what Eric wanted to do is say, well, given the entire code base, how toxic is the code base? Take into account all these cumulative values, and in fact, which are the most toxic classes in the code base. And so he wrote a little utility, and this is all on his website, that basically went through, CheckStyle is just a command line tool, went through and ran this analysis, and then consolidated all this data into, wrote a script to push this all into comma separated values, and then pull that into Excel, and then created a graph from it to be able to show this relationship in that code. Eric has also produced some really interesting graphs for things like cyclomatic complexity per line of code. This is a good example of something you might generate as part of a regular build cycle. This shows cyclomatic complexity per line of code. This is from a real code base from April 1st, 2006 to August 18th, 2007, and shows the rise and fall of cyclomatic complexity per line of code. And they actually took actions in this code base based on this. This was the first go live release of this code, and because they had a lot of volatility here and it was creeping up at an alarming rate, they decided to take some action, and 3.0 and 3.1 were maintenance releases to clean up a lot of that technical debt. So they're using this to guide the behavior on the project, which is of course the idea you want from something like an information radiator. The other way that you tend to use metrics tools in this world is probes. Like I said, you take off at an ultralight and you're converting it into a 747 in the air, you need to be able to understand what's happening with that code as it's being built. You don't have the luxury of spending weeks or months up front thinking about how all the structural components fit together, because you're building the components and kind of fitting them together at the same time. There are some standard visualization tools out there, but there's a couple of really interesting ones, again, mostly in the Java space, but there are some .NET analogs for this. One of these is this tool X-Ray, which is inspired by an old school Smalltalk tool. Actually, CodeCrawler is still available on Smalltalk, and the Smalltalk guys invented some of the first really cool metrics and visualization tools. They were the first ones to really do object-oriented coding at an industrial scale, so much so that they built a meta platform for metrics called Moose. And all of the Smalltalk metrics tools accept Moose metadata. And so you can, if you're using some language like Java or C# or some more exotic language like C++, if you can produce Moose metadata, you can produce these kind of visualizations with the Smalltalk code crawler. So there are a variety of metrics tools in the Java and the .NET world that will take your Java code, produce Moose metadata, and then you can slurp that code right into these tools like this. This one is especially designed for Java, but based on the tool code crawler that's available in the Smalltalk world. And the idea behind X-Ray is you're looking at an entire code base here where the lines indicate inheritance relationships. The length of the box is the number of lines of code, and the width of the box is the number of methods. And so if you zoom in on a piece of the code base here, just knowing the way that you construct the boxes here, that would make me very curious to go have a look at this class and this class. Lots of lines of code, very few methods. I don't really like that shape very much in my code base. I like squarer things, not such long, skinny things, because that suggests that you have lots of very long methods in here, which is kind of a code smell. And so this is kind of an interesting view of a code base, but the more useful view for X-Ray for us from an architecture standpoint is the way that you can look at dependencies between things in this world. And I have a much better projector today. I showed a few of these yesterday on a really hideous projector downstairs. This one is much better. And you can see a lot more of the detail in these diagrams. So in X-Ray, when you click on a particular class, it will show you the afferent and efferent coupling from that class. The arrowheads will show you whether it's afferent or efferent. And the weight of the arrow indicates the strength of the connection between these things. And so you can see here that there are 3 highly coupled classes of this one, another one that's medium coupled, and then a double handful of very lightly coupled things to this class. So that's a kind of an interesting view. This allows you on a class-by-class basis to say, how coupled is this class to the rest of the world? How much of the rest of the world uses this? Which is kind of interesting from an investigatory standpoint. But you can also get a pie chart view of the entire world, and this becomes more interesting when you start thinking about decomposing things. So this is a package view of a particular class, a particular project, and then this is a class view of that exact same project. Now, this is a relatively simple project, so you don't have a giant amount of stuff going on here, but notice that X-Ray, when it does this, always produces the same picture, so you can use this consistently to do some analysis on this. Notice that if, for example, let's just say this is a crazy hypothetical because I'm sure no one here is in this situation of having a monolith which you're trying to kind of decompose into smaller and smaller services or smaller and smaller pieces. You know, just a hypothetical. I'm sure nobody's really trying to do that or anything. When you produce one of these diagrams, the observation is that the more of these bold red lines I cut as I decompose that monolith, the harder I'm making my life. Because those are coupling points. And the more of these that I snip, the more I've got to shore up those coupling points and figure out, okay, these two things used to call one another. Now, how are they going to handle this job? And so if I were looking at this purely from a decomposition standpoint, my first instinct would be to say, you know what? If I had this monolith and I need to cut it down into smaller pieces, the first piece might be, can I just slice all this part off as one big service? Because now I'm slicing the fewest bold red lines when I do that, and so structurally at least, it's going to be way easier to make that transition. It may run afoul of other kinds of coupling, like temporal coupling or something like that, which I'll talk about later, but at least from a structural standpoint, you can kind of see how much things are coupled to one another, and that becomes some interesting information when you start thinking about decomposing things. This is a more realistic picture from a real project. This is Argo UML, which is an open source UML mapping tool, and it's Java-based. And this is its class diagram from Argo UML. Obviously, a lot going on there. This falls into the hazard of tools like this, what I refer to as the hairball effect. Once you get a certain level of information density, it becomes hard to get real information out of it. You can filter this down in X-Ray, which makes it more useful. And this is the package view from the same project. And of course, this is running inside Eclipse. This is an Eclipse plugin. So if you click on one of these, you go right to that code and see what's going on with it. So that's X-Ray. Let me show you one other tool. And this one is kind of fanciful, but it does have some interesting uses as well. This is also inspired by an old school Smalltalk tool. This is called Code City. It's an open source tool that will take your code base and convert it into a 3D cityscape that you can fly around as if in a helicopter. So each of these buildings is a class. We follow the same rules as X-ray, where the height of the building is the number of lines of code and the width of the base is the number of methods in that class. And the neighborhoods are packages or namespaces. And so you can take your code base and kind of fly around inside it if you want to see what it looks like. There's my code base. There's one really bad class there, that tower. It looks like an airplane hazard. This is from the airplane straight down above you. So that would be just kind of cool, but you can also turn on some colors here. So I'm turning on brain classes, which are in yellow, and God classes, which are in red. So a God object is an object that knows too much or does too much, and those are highlighted in red here. Those are objects that typically have really high afferent and or efferent coupling. What kind of classes should have high afferent and or efferent coupling? Controllers, workflow components, the things that herd all these other model objects together and make them do stuff and then send them off to a view somewhere. And so if you turn on God objects here and it lights up non-controllers, then you may want to look into those to say, are you really more complex? Do you know you have way too much coupling? Have I got my structural partitioning wrong because you're so coupled to the things around you? Maybe that all should be one thing. Those are God objects. Brain classes are ones that have really high cyclomatic complexity. So you could look at those and say, are those too complex, or is it essential versus accidental complexity, that sort of stuff. The other thing you can do with Code City is snapshots in time. I wish you could do any arbitrary time. You can't. You have to go in and say, I want a snapshot at this point in time. But this allows you to see the code base kind of grow over time and evolve. But something weird happened here. I want to go back for a second and talk about this neighborhood right here. So there was a point in time where it didn't exist, and then all of a sudden, it existed. So given the rules of how we know how Code City builds buildings, what is this weird little neighborhood that has popped up over here? What do you think? It could be that a bunch of C programmers have joined my Java project that they don't understand, object-oriented programming. They're all building big, static methods or something like that, but that's not it. Anybody? It's code generation. Code generators, when they run, typically build things in their own package and namespace, and they typically build classes that have almost no methods in them and a whole bunch of generated code, and it's all boilerplate, so it's tons and tons of code. That's what creates this weird little neighborhood that you see here. Now, if you're the architect on a project and you're not expecting code generation to happen, and this pops up at some point while you're in mid-flight, you may say, oh, wait a minute, this is kind of odd. Let's go investigate what's going on here. Sometimes having tools that allow you to see code at a coarser grain level than the source code itself is really useful because you can see patterns and correlations and other things in some of these visualizations. Having said that, we still have a lot of very serious limitations in metrics in the software world. We would like for these to be a much stronger analytical tool than they are, but we're kind of behind the gun because we've only been doing software for real for 100 years or so. We're basically at the point where civil engineers were, where they'd build a bridge, roll something heavy over it, when it collapsed, they'd say, well, that was kind of a crappy bridge, let's try again and see if we can build a better bridge. That's kind of where we are in engineering sophistication now. So while we love metrics, they suffer from a lot of limitations. There's a signal-to-noise problem in that you may have a really interesting metric and it's telling you something, but there's a noisy metric very close by that's drowning out the interesting part, and so it's hard to figure out which one is the more pertinent value. The other problem is there's no one true metric that tells you tons of things about a code base. There's nothing anywhere near kind of the tools that they have in the statics and dynamics world for structural engineering. Even really useful metrics like cyclomatic complexity can't tell you, is this essential or is it accidental complexity? All it can say is it's complex, and you still have to figure out, should it be there or not? So they're very blunt instruments at best. Another problem is you gather a bunch of metrics and then you ignore them. I refer to this as the sonar problem because it has a really nice plug-in from Maven, and you wire it all up and generate a bunch of metrics like, wow, this is cool. And you forget about them for like a year, and you go back and say, look, we've been generating metrics for a year, and it says our code base sucks, and it's too late to do anything about it. So that's a problem. Inaction and overaction are both problems. Inaction for obvious reasons. You gather these things and never use them as part of your feedback loop to actually act on them. In fact, the way that we typically consume metrics on projects when I am the tech lead or architect is that we typically have, our usual is we have 2-week iterations, and we have an iteration planning meeting every 2 weeks. Just after that iteration planning meeting, we typically have a developer huddle, which is half an hour, 45 minutes of just developers and technical people. And that's when we go over things like trends and metrics and things, thresholds and things that we need to watch out for and other things that need to be acted on. So that's a way to avoid inaction. The other problem is overaction. And this highlights a problem that I point out at great length in my continuous delivery talk, is that one of the problems you have with developers is, so let's say when you really boil it down to its essence, and in your heart of hearts, when you're trying to describe your job to your grandmother, it pretty much very often boils down to I take things from a web page and put them in a relational database, and I take things from a relational database and put them on a web page. I mean, there's a little more sophistication in there, but you know, when you really boil it down, a lot of times that's what it ends up being. The problem is, after you've done that for 20 or 30 or 40 times, that gets kind of boring. You know what developers do when their day job is boring? They invent cool puzzles to solve at work so that they have meaty puzzles to solve when they come into work every day. I call this problem meta work is more interesting than work. And metrics will definitely fall into this problem that you get your developers really excited about some metric like 100% code coverage, and they will start gaming that to the point of insanity, because that becomes the new puzzle to solve at work, not making things work the way they're supposed to, but this is the thing you can really sink your teeth into, because the thing you're doing for your day job is not very exciting, but man, we can make this exciting. So you have to be careful not to get people too excited about metrics, or they will go completely nuts and overboard. And very often in this world, you want to prefer trends to discrete values. Things like cyclomatic complexity, you look at that and say, well, I have a method that has a cyclomatic complexity of 12. Is that good or bad? I don't know, it may be doing a lot of really legitimate stuff, but if you look at it now and it's 12, and you look at it again in a month and it's 20, and then in a month later it's 35, clearly it's going in a bad direction. Just to see if you can tamper that down. That's why a lot of these visualization tools like Sonar are really cool, because they'll give you things like trending over time. This is complexity over complexity per method in the struts code base, and you'll see something horrible happens to it around the 1st of September in 2009 when they merged another code base in that was really kind of a train wreck. And you can see from a metric standpoint exactly when that happened, and it's a nice bouncing ball too to show your boss. Okay. So that's enough backgroundy kind of stuff. Let's talk now about component-based architectures. The Continuous Delivery book, when it came out in 2010, actually said very little about architecture. Mostly it was about engineering practices like testing and DevOps, et cetera. But there are a lot of interesting architectural things here as well. And this is really the only piece of advice they directly give in the book, to use components to decouple parts of your application that change at different rates. And this is one of the criteria that you use to decide what are the partitioning points to break things into components. A component is too broad because we really have two kinds of components that we regularly deal with in the software world, either libraries or services. Libraries run within a single process and communicate through language function call mechanisms. These are internal libraries. These are the frameworks and the jar files and the DLLs and the Ruby gems. These are all compile time dependencies. They have a whole set of engineering practices to go with them. The other things are services. Services tend to run in separate processes and communicate through integration architecture mechanisms like HTTP or TCP/IP or higher level protocols on top of that, like SOAP or REST or something like that. So let's talk about each of these things in turn, and let's first talk about some things around components in this world. So like I said, most of the continuous delivery literature kind of assumes that you're building monolithic applications, but let's say that you want to break that monolith down and build it as a series of libraries as well that contribute to the application. And so the idea here is we have a framework, we have a reports engine, settlement engine, pricing engine. They all build toward the portfolio management application. And then you have this third-party library that comes from the internet somewhere. It's a jar file or DLL or something like that that you download as a component of your system. So let's talk about a few engineering challenges here. And the first of these, of course, is managing dependencies. And most people's first real encounter with this was this friendly thing called DLL hell that used to exist in Windows. But I bring this up here not just from a dependency standpoint, but it also completely exemplifies my earlier contention that we constantly build outdated architectures. Yesterday's best practice is tomorrow's anti-pattern. Because think about why DLLs existed. They existed because in the very, very early days of Windows, hard drives were very small, 10 megabytes or 20 megabytes. They didn't have room to statically link all that code together to make all those applications, so they came up with an architecture that said, well, we'll share all these libraries that are common across all these controls, again, toward this architectural goal of absolute, singular purity, have one source of truth for those things. But of course, the problem is different people's one source of truth became different things as updates happen, and you get these transitive dependency management problems. The limitation that led them to that design disappeared within the first 5 or 6 years of its life, but the architectural limitation persisted for like 20 years before they finally chased it away with .NET and the way their components worked. But from a realistic standpoint now, people have two approaches to tackling this on projects. The ubiquitous lib directory where you put all of your dependencies and everybody feels free to add stuff all the time, but everybody is terrified from removing anything from this library because you might accidentally destroy the earth if you did that. Or some sort of transitive dependency management tool, and everybody always ends up with some sort of transitive dependency management tool because this is just too hard a problem to solve otherwise. So every platform has one of these now. We have Maven and Ivy in the Java world, and NuGet in the .NET world, and Bundler in the Ruby world, and Pip and Fabric in the Python world, and Grunt and Gulp in the JavaScript world. So all these things exist in every platform now. So let's talk about some anti-patterns around components. And this one is really quite common, circular dependencies. When you have a class that relies on another class, which relies on another class, it comes back and it relies on the original class. This is really super common in languages that have really powerful IDEs, like Java and .NET. Because what happens is you're tooling along in your IDE and you reference some class that you've never referenced before that is conceptually 100,000 miles away. What does your IDE do as soon as it recognizes that? It pops up a friendly dialog that says, do you want me to auto-import that class for you? And you swat that away so fast you never even realized it happened. If somebody came 5 minutes later and said, hey, did you just auto-import something? You'd say, no, I haven't auto-imported anything for like an hour or so. Because it's just a reflex now. You swat that dialog like a fly, never even think about it. What you really need is some sort of obnoxious Clippy-like thing that pops up in your IDE that says, should you be importing this class from all the way over there? Should you think about this? Are you really creating a cycle in your code base if you do this? The problem with cycles is it makes things really hard to componentize because these things all become tangled up together, and it makes your life cycle a lot more complicated. So let's talk about some tools to get rid of this. This is one in the Java world called Jar Analyzer. This is an open source tool that you can run against a directory of jar files, and it will tell you how those things are coupled to one another. It will give them afferent and efferent coupling ratings against one another in a matrix so you can see how things are coupled to one another. But it also uses the open source GraphViz graphing library to graph the relationship between those dependencies. And so, for example, here's from struts 1.0, the dependencies between the components that make up struts. This can become a real problem in Java if you ignore this problem, and I give as my evidence to that the exact same diagram for struts version 2. Yikes, that's terrifying. This is what happens if you ignore this problem in the Java world. You end up with an exuberantly coupled system that would be extremely hard to componentize now because everything relates to everything else. So let's talk about getting rid of that. This is the only commercial tool that I talk about here. This one is specifically for Java, but there's an analog in the .NET world as well. This is a tool called Structure 101 that goes through and analyzes your code base and looks for cycles. It gives you a to-do list of refactorings, and if you do those refactorings, then you will have eliminated that cycle. What this does is allow developers to go through their code and gradually, slowly untangle cycles. If you look at a component-based framework that is almost legendarily clean in terms of metrics and particularly cycles, Spring and all the related pieces of Spring. And that's not coincidental. All the Spring committers run Structure 101 on their laptops, and before they make major commits, they make sure they haven't accidentally introduced cycles, because it's so easy to do this because the tooling in this world just makes it automatic to produce cycles. And so kind of step one is to go through, find the cycles in your code base and untangle them. There's a similar commercial tool in the .NET space called Independ that also shows you the relationship between afferent and efferent coupling between all your components, and also does some cycle analysis. It doesn't do the same to-do list kind of thing, but you can use the same tool in the .NET ecosystem to untangle cycles in your code base as well. But once you've untangled them, what's going to prevent them from coming back? So one thing you could do is explain this problem to your developers, and then keep a close eye on a code review, and then as soon as they start importing things they shouldn't, have public meetings at noon on Friday. So that's one way to handle this problem, but I think we can come up with a better way to handle this problem. I hate setting up situations where developers have to keep something in the forefront of their mind all the time when it's not really part of their day job. This is kind of an incidental part of their day job. So what I want to set up are some engineering safety nets. So this is a really useful thing in the Java ecosystem. There's a metrics tool called JDepend that's been around for quite a long time, that's written in Java, that will tell you afferent dependencies between packages. But because it's written in Java, it can also understand parts of the Java ecosystem. And in fact, what you can do is put this unit test in place on your project once you've gotten rid of all your cycles. Tell it, go gather all the packages in the project, and then tell me if there are any cycles or not. This will fail this unit test if any cycles exist in your code base. So the trick now is, as the architect, you go through and chase away the cycles, and then put this unit test in place so that if somebody tries to inadvertently add a cycle because a tool has been too helpful, you failed this unit test before it actually gets into your code base. This is setting up kind of an engineering safety net to make sure that something is being too helpful on one side. Let's set up a safety net to make sure that extra helpfulness doesn't end up having a detrimental effect on the code that we produce. You can also use JDepend to wire up some architectural rules in your project. For example, let's say that you have 3 packages here, EJB, Web, and Util, and it's okay for EJB to depend upon Util, and it's okay for Web to depend upon Util, but I never want the reverse to happen. I never want Util to rely on Web, for example, because that would be kind of a logical fallacy. So you could wire up the way dependencies are supposed to work here, and then tell JDepend analyze, and it will tell you if any of those rules have been violated. This is the kind of thing you can set up as an architect on a project that's doing something like continuous delivery, where you are running unit tests on a regular basis every time you do a check-in. This sets up an engineering safety net to say, okay, I've established some rules about the way I want the direction of things to work in this code base, and now I can set up a safety check to make sure that if people accidentally do that, then they're notified. Questions about that so far? Yes?
Can I ask, the cyclic dependency, would that cover catching, say, a customer depends on order, or order depends on customer?
Yes. Yep, that's circular dependency. This I'm not sure about. Certainly you could build a tool like this because you can use reflection to learn all this stuff. And my guess is that someone has, I just don't know about it. So it would be worth doing a search for that because it's a really useful thing.
What's the difference between this to, for instance, getting a layer diagram and validating the architecture?
I'm sorry, what's the difference between this and?
If you have a layer diagram in your project that you validate the architecture, what's the difference?
Well, so if you have a layer diagram that you validate in your project, somebody has to do that every time you want to do that, whereas now every single time somebody touches the code base, this runs as part of a cycle. So now a person doesn't have to go chase this down. You literally never gets into your code base because you fail a unit test before it ever gets into your code base. So this is a much more proactive way of doing that. This again goes toward that continuous delivery idea of find the eagerest way to do things, because that's the least painful from an engineering standpoint very often, is the quickest way to catch those things. So what we really want to get to in this world is the ability to pipeline libraries together to say that this component builds in this component. And in fact, deployment pipeline tools allow you to set up these kinds of scenarios where make sure all three of these are built correctly before you build the next thing, and you can control dependencies that way. That's exactly the thing that we want to set up as we automatically build things in something like a deployment pipeline. Here's another anti-pattern that's quite common in the component world. So let's say that we've made a change to framework, and all of its unit tests are good. Because it has changed, all of its downstream components wants to incorporate that change. So reports engine incorporates that change, and it's happy with it. All of its tests are green. But when pricing engine tries to incorporate that change, it cannot. All of its tests are now red. Now the $64,000 question is, which version of framework should the portfolio management application depend on? And of course, the answer is none of the above. There is no legal ancestor for it to depend on because two of its upstream dependencies have different dependencies. This is a problem in the internet at large because you can't control the build order of things, and so you have to manage this in a different way. If you control the build order of things, you can solve this diamond dependency problem, just like this. So in this world, what we would do in our deployment pipeline is set up so that when framework undergoes a change, it builds itself. That will trigger a build for the three engines, and only if all three of those are successful does it try to promote and then build the application itself. So make sure you resolve all dependencies at one level before you try to resolve the next level of dependencies. And that'll keep you out of this diamond dependency problem, and in fact allow you to build things quite incrementally. So that's all stuff about components. Let's now talk about services. Now I'll talk about a few prefer things here. This is using the Agile Manifesto's rhetorical technique of prefer the thing to the left of the thing on the right, which is not to say the thing on the right has no value. We just like the thing on the left more for various reasons. And in this world, we tend to prefer choreography to orchestration. And here's what I mean by that. In the traditional kind of service-oriented architecture, enterprise service bus kind of pattern, the idea is that these services have a bunch of common shared functionality. They need to know how to talk to one another. They will often frequently need to transform data from one format to another as you make calls between these services. You need to be able to orchestrate services together to perform business functions and things like that. And so in the traditional kind of SOA ESB pattern, the idea was, let's take all that common functionality, move it out to the middle here where it can be managed separately from the other stuff. Again, this is toward this kind of architectural impulse to let's commonize things that are going to be alike and put them in one useful place. This is referred to as an orchestration style of integration architecture because the enterprise service bus or broker there is acting as the conductor of the orchestra. Any service that needs to do something has to check with the conductor to see if it's okay to do that because it coordinates all the stuff. The contrast to that is a choreography style of integration architecture where there is no third-party arbiter. All the behavior that you want is inside each one of these services, including any kind of routing or transformation or any sort of behavior like that is completely self-contained within each one of these services. Because increasingly, when we think about services like this, we think about them with a particular perspective. And I have slides here in just a second, I believe, that talks about that. A particular perspective on this where we want these services, oops, sorry, I started that slide over. We want these services to be completely self-contained. Oh, sorry, Keynote does this now. If you ever try to navigate or check something, stops wanting to cooperate. So we talked about orchestration. We prefer choreography where each of these services is completely self-contained. For reasons I'll get into as I start talking about the kind of philosophy around services and particularly microservices, what we're trying to avoid here is because we're going to operationalize this thing as a service, and so everything it knows is going to be completely encapsulated inside it. This is this domain-driven design concept of bounded context. And our complaint about this style of architecture is that because part of the behavior that should belong inside that service, things like data transformation and other sort of logic, are now separated from that service, kind of smeared across integration architecture. We really would prefer these services to be completely self-contained, because one of the things that we're trying to support here is to allow these services to evolve completely independently of one another, not be coupled to one another incidentally through something like an enterprise service bus. A couple of side effects of this. Something I'll talk about in a second is this phenomenon called Conway's Law. Conway's Law pretty much guarantees that you will have a bunch of enterprise architects that will accrue around your enterprise service bus because communication structures end up creating layers in architecture from a technical standpoint. The other side effect over here is, so what I'm trying to set up is an architecture that allows individual services to evolve completely independently of one another. But they also need to integrate with one another because they need to cooperate to form business tasks and other things like that. So how can I meet the dual goals of allowing them to integrate, to evolve as aggressively as possible, but not break the integration points that I've established between these services if I don't have some third-party arbiter to do that for me? This, again, we fall back on engineering practices in the continuous delivery world, and the engineering practice here is this thing called consumer-driven contracts. So the idea of consumer-driven contracts, let's say that you have a service provider, which is this team on the left, and there are 3 other teams who want to consume whatever information that guy is providing. The idea of consumer-driven contracts is that these 2 teams will get together and they will arrive on a shared set of unit tests and mostly be driven by these guys. So the idea of consumer-driven contract is these guys are going to put together a set of unit and integration tests and hand them over to these guys, and these guys promise I will run those tests and keep them green every time I make a change to my code. We're going to do that for all 3 of these teams. So this team is going to put together a set of unit and integration tests and encapsulates what they need from that service provider and hand them those tests. So this team is now running 3 other sets of unit integration tests as part of their normal build cycle to make sure those contracts stay intact. If this guy changes and doesn't break any of those tests, then everything's cool. I can evolve in any way that I want that doesn't break a test. If a day comes where I need to evolve in a way that will break one of these tests, that becomes a placeholder for conversation between those 2 teams again. Let's get together and figure out how we can unify this and rebuild these tests so that we can keep those contracts intact even though we're changing. This is a good idea of putting engineering practice in place to make sure that you haven't violated something like an integration point between 2 things and yet still allow them to evolve at more or less independent rates. Another one of the things in this service-based world is we tend to prefer REST over SOAP. SOAP is at its heart a remote procedure call mechanism which does strict parameter binding, and if the parameters don't match exactly, then things don't work well. This is a good example of a kind of a 3-dimensional architecture that is not a good 4-dimensional architecture, because you can build a SOAP system with very highly coupled endpoints, but now as you start needing to evolve those endpoints, you're constantly breaking them and having to reestablish them. That's why REST works a little better in this world, because it's resource-based rather than being RPC-based. So in the REST world, I'm just going after resources and pieces of resources. So for example, if I'm using a resource and digging into it and getting information about airline seats, when they augment that resource and add things like engines and wings and all that stuff to it, it doesn't invalidate my other requests to get resources and information about seats, because I'm just adding in a natural kind of evolutionary way. It's also a little bit better to do looser parameter binding at endpoints in the REST world. So we tend to like this a little better because it's a little more malleable at integration points. And we find that in integration architecture, a little bit of malleability helps. A lot of times very strict binding breaks inadvertently in ways that is unpleasant. This doesn't mean you can't be successful with SOAP. It just seems that REST models this problem a little better. So let's talk about some characteristics of services, but also microservices. So you hear a lot of talk about microservices as a very popular style of architecture right now, but it's really just a variation in the service-based architectures that we've known about for a long time. The main difference between what we've thought about as service-based architectures and SOA and microservices, the main difference is that in the microservice world, they've completely embraced the operational aspects of the architecture. So microservices is quite interesting because it's the first post-DevOps revolution architecture. It's the first architecture that fully takes into account all the things that it takes to actually operationalize the architecture as well, and makes that a first-class citizen in the architecture. People like Netflix and Amazon have showed that architecture can actually be used as a business tool if you build a sophisticated enough architecture. And every architecture going forward is going to have to accommodate all these operational constraints. This just happens to be the first one to do that. And that's the real difference between what we think of as traditional service-based architecture, which is still the kind of traditional shared infrastructure kind of architecture, versus microservice, where everything is this kind of encapsulated, bounded context. And in fact, these are the ideas that I was talking about from domain-driven design, which is ostensibly an object modeling technique that Eric Evans came up with, and there are some more concrete implementation details to be found there. But there's this really cool concept that we like from the domain-driven design world called a bounded context. So when you identify a domain in domain-driven design, it is a bounded context, meaning that everything that it knows about its implementation is encapsulated inside that bounded context. Other bounded contexts can get information from it, but it has to be some sort of messaging or something like that. No bounded context knows the internal details of any other bounded context. And when you take this concept and combine it with continuous delivery, what we see is that we're actually reifying this bounded context idea in architecture. So services in a microservices world are bounded context, meaning that if they have persistence, they own their own persistence mechanism. They own their own database. They're responsible for the schema. They're responsible from an operational standpoint of backing it up. A DBA there is responsible for schema evolution and all that stuff, but it is completely encapsulated within that service. This goes toward the main goal in the microservices world, which means that change is really, really easy in that world. One of the big constraints of having a bunch of shared infrastructure style architecture is that isolated change is hard and expensive. In fact, one of the defining characteristics for software architecture for the past 15 years has been the things that are hard to change later. Well, microservices is changing that because you are thinking about the entire details of how you operationalize it. Change is relatively easy because all the operational impacts of that change are already thought about and already worked into the architecture. So the big difference between a services-based architecture and a microservices from this standpoint is that you may not have as encapsulated a boundary in a services-based architecture as in a microservices-based architecture. So when we talk about services, we talk about monoliths versus services to some level of degree of decomposition. We talk about monolithic architectures. You're talking about using shared resources, running multiple things in the same kind of containers. Microservices tend to run in their own processes and be completely self-contained within their own process. Monoliths, when you want to scale them, you tend to take containers and cluster them together and build protocols at the application server level to handle that. Whereas in the microservices world, if you need scalability, you just spin up more versions of microservices. But this is a good example of this perspective shift that I was talking about before. Because really, scalability should be an operational concern. Operations is the one that owns machinery and resources. They should be the one to think about and worry about, like scalability on demand and that sort of stuff. But this kind of architecture treats operations like the weather. It's something that you have to endure and you can't really make any changes to it, and so we'll just work around them. And so a lot of scalability and other kind of protocols, clustering protocols, are built in the tooling at this level, whereas over here we say let the operation part of the architecture handle that, and you can build a lot simpler pieces here because they're not relying on all the sophistication to handle things like clustering and load balancing and all that stuff. You can handle that at the operational level. So I mentioned Conway's law before as I was talking about choreography versus orchestration. And this is Conway's law. This is an observation that Melvin Conway made back in 1968, which is one of those kind of obvious in hindsight observations, that any organization which designs a system will produce a design whose structure is a copy of that organization's communication structure. Besides being a tad wordier than he should be, what he's observing here is that when you have a communication structure in an organization and they design systems, the system design will tend to resemble the communication structure that exists inside the organization. That's the thing that suggests if you have specialists in your architecture, like UI specialists and middleware specialists and DBAs, you will end up with those layers in your architecture. So it's a natural kind of consequence of the way communication streams work on software projects. This is a cartoon I found about Conway's Law, and I reproduced it here because it's shockingly accurate in many cases. So Amazon really does have this really super fine-grained kind of structure for their teams, which I'll talk about in a second, 2 pizza teams. And Google really does have a very convoluted communication structure like this. And this is reflected in their architectures. Google hates transitive dependencies. They love building big fat executables where all the dependencies are resolved at compile time, which is why they love C++ and Go, which is a compiled language. They like managing all those things up front and having things that are completely self-contained, whereas Amazon has become the master of transitive dependency management. That's kind of what they do, and they also sell books. But mostly they do transitive dependency management like kings. And of course, I think Oracle's funny here with the legal department is mostly versus the engineering department. What Conway's Law suggests is that most people end up structuring teams like this because it's natural from a human resources standpoint to say like things flock together. So, you know, all those user interface people, they all have tattoos and piercings, so let's put them in one set of offices. And, you know, the server-side guys all have neck beards, let's put them in one set of offices. And, you know, it's easy to partition people like that. What we're suggesting in this world is something that we're calling the inverse Conway maneuver, where you build domain-specific cross-functional teams. This is quite common in a services or microservices-based world where you have cross-functional teams that manage the domain thing, the service that you're trying to build. That has some interesting beneficial side effects. One of them is this perspective that you see talked about in the world of products over projects. The kind of anti-pattern for projects in big corporations is you have a group of developers who work on something up until a time when it is deemed done and shipped, and they pass that over to someone in operations, and then operations takes care of the care and feeding of that for the rest of its life. It's hard to get maintenance and changes and things like that for it because this team is disbanded, moved on to another project, and don't even remember writing that code from that old project from 2 years ago. There's no real ownership there. One of the things that Amazon has done is they've taken this idea of 2 pizza teams. That's what they call each team at Amazon. No team shall be larger than it can be fed with 2 large pizzas. So from a practical standpoint, that's about 12 people is the largest team of engineers at Amazon. And they're all these highly cross-functional teams, and they're product teams, not project teams. And the difference there is that this product team owns a product within the Amazon ecosystem. Maybe they own the New York Times bestseller product within the ecosystem. That means that they have developers and business analysts and a product owner as part of this product team, and they have a DBA and an operations person, and the operations person on this team puts it into production for them, and this team owns that in production forever. There's never an expiration date on this because this is your product. This is the thing that you own as part of your job at Amazon. Each of these teams is completely autonomous and responsible for putting their own stuff into production, and the product owner is responsible for proselytizing this product within the overall Amazon ecosystem. So they're going to go and see what other services within Amazon would like to consume from their service as a product. This has a bunch of interesting side effects because this brings social pressure to bear on projects. This whole 12 people thing is not coincidental. This is kind of a natural partitioning of groups of humans. They think pre-verbal hunting parties were about this size. Most sports teams are about that size. This is a natural kind of partitioning of people. But it also helps you pull in social constructs. So let's say that you're in this more traditional world here, and you wrote some terrible code that blew up in the middle of the night, and someone from operations got paged and had to go fix some train wreck you created. You're very detached from that from a day-to-day job standpoint. Maybe you get an email the next morning that explains that something went wrong. But if you're on one of these 2 pizza teams at Amazon and something goes wrong in the middle of the night, somebody on your team got paged and had to get up and go fix it, and you have to look across the breakfast table at their sad, tired eyes the next morning, it's going to make you a more responsible developer because it has now an immediate impact on somebody that's part of your team, not some voiceless, faceless person that's in some silo somewhere in your organization. It's somebody that's on your team that you know on a regular basis. You're going to try to do a better job on their behalf. Another characteristic of a lot of these services and microservices architectures are smart endpoints and dumb pipes. We're trying to become as decoupled and cohesive as possible here, and inspired by the way that things like Unix pipes and filters work. The transport in this world is typically something like HTTP because it's nice and transparent, or messaging over a lightweight bus if we need to go to binary. Now, I said bad things about things like an enterprise service bus earlier. I will amend that by saying that if you're using your enterprise service bus purely for plumbing, then we're okay with it. The reason we don't like that enterprise service bus concept is it violates that bounded context idea where everything that a service knows or does should be encapsulated inside its bounded context. If you're taking some of its behavior and smearing it out across your integration architecture, you've violated bounded context. But if you're using an enterprise service bus just as a pipe, then we're okay with it because you haven't violated that rule. Another common characteristic in this world is decentralized data management. When you have monoliths and you're talking to monolithic databases, it's very easy to do things like transactional behavior because it's well supported within the monolith and the frameworks that support the monolith. But when you get to a more services and microservices based world, that becomes a lot trickier thing. Even in a services world, you are mostly in an eventual consistency kind of world, not a transactional kind of world. You will eventually always be in an eventual consistency kind of world because as you get more and more distribution for your data, you reach a point where you can no longer guarantee all 4 properties of ACID. That's the CAP theorem, so you always end up, when you hit a certain scale, going to eventual consistency. You have to get there a lot faster in this world. Now, if you're in just a services world, you're probably still sharing a database like this and you have individual services. In a microservices world, each of these services is its own bounded context, meaning that it owns its own data and persistence if it persists data. That means that there's a DBA on this little cross-functional team and there's an operations person who knows how to spin that up, et cetera. And transactions are a lot more difficult in this world and you try to avoid them like the plague. Now, having said that, there are still some situations that are legitimately transactional in the world. You just can't get away from those things. And so it is not considered a complete war crime if you do cheat a little bit and have 2 microservices, maybe share a transactional context around a single database. This is one of those architectural purity versus pragmatism kind of arguments. The example that I gave yesterday that I typically give in this case is that there is something like 7 normal forms in relational databases, and if you really are a dyed-in-the-wool relational database person, you go to all 7 normal forms, which nobody ever does. You get to about 3rd normal form and you say, you know what, that's good enough, because while the philosophy is cool, it's now becoming cumbersome. That's the same thing here, particularly if you're in an evolutionary situation where you're evolving from monolith to services, you may keep some of those in place as known exceptions to the purity of the architecture just from a pragmatic standpoint so you don't end up doing something crazy like trying to wire up distributed transactions. Another beneficial side effect, particularly of this whole bounded context idea, is that you don't get ripple effects of changes. So let's say that this team is the customer team, and they're building a customer microservice which says that they own their own persistence. And they decide, you know what, we're going to use Mongo for this because this team is responsible for spinning up their own relational database instance and managing the data and all that stuff. And maybe the operations person on this team has looked around and noticed that, you know what, I can take Mongo from a raw IP address to running instance of Mongo in about 90 seconds flat, and I'm pretty sure you cannot get the first Oracle install dialog to come up in just 90 seconds. And so they've decided, you know what, we don't need the bazooka, the atomic bomb that is Oracle from a data standpoint. I just need simple persistence. And so you put Mongo in place and operationalize it yourself. And it turns out it was a terrible idea. 6 months later, it's like, oh, what a nightmare. We need to change to Postgres. And you change to Postgres, and nobody else cares because nobody else is coupled to that infrastructure. This is the beauty of microservices. This is why change is a first-class citizen in this world, because nobody else is coupled to that decision, nobody else cares, and so each of these teams is allowed to make their own decisions about things. Now, we're not suggesting a world here where everybody's allowed to just go crazy and pick their own technology stacks, but we also observe a world where a lot of people are being forced to use tools that are way more complex and sophisticated than the code they're writing just because they're being forced to share all that infrastructure. If there's only a single database server I can choose for my organization because everybody has to share that, I have to pick the one that handles every edge case, which means I have to get the industrial strength nuclear option in enterprise database server. But most of your problems, 90% of your problems, don't need, and in fact is overkill to use something as sophisticated as that. This allows you to right-size technology choices for the problem you're trying to solve inside your ecosystem. That's the idea. So let's talk about some benefits of this kind of services and microservices kind of world. And here's an example of that. So let's say you have a bunch of services and or microservices running around, and you need to draw a page. Now let's say this is a commercial site like Amazon, for example, and a user requests something. We send out a bunch of requests to those services and we start a clock. The clock is really important because for a site like Amazon, I don't know what the exact number is, but you can bet that they've done market research and they can tell you the exact cutover point where the richness of the page takes too long to draw that makes some percentage of customers get bored and wander away. So they know exactly how long they have to draw the richest page possible that preserves the most number of customers. They've done this market research to do that, so the clock's very important. So when they send off those requests, some of these guys will start sending results back. We don't draw anything yet, but this guy starts aggregating those results and start planning about how we're going to draw a page. And at some point, the clock expires. It's done. It's time to draw the page. We render the page. Some of these services may still send stuff back, but you know, sorry, you're too late. Maybe next time you'll get in fast enough, but the SLA to draw the page is more important than getting the most recent accurate information from that, whatever that service was. And so in this world, timely partial results are more interesting than slow complete results, because we're trying to work against a service level agreement for being able to draw a page here. And so, for example, maybe one of these calls, maybe one of the things I want to put on the home page is New York Times bestseller list. So as soon as I make that first request, it sends out two service requests, one to the cached New York Times bestseller list service and the other to the live bestseller list service. The cached one comes back right away, and I plan to put that on the page. If the live one comes back in time, I'll replace the cached one with the live one, but if it doesn't, you get the cached one on the home page. If you really want that, you click through it and get the real thing, and you'll wait long enough to get that. The other side effect of this is that returns here are optimized for ranking and aggregation, not display. These are all data structures that come back. This guy is responsible for actually drawing the page and deciding what elements to put on there and what ordering and all that stuff happens. When you operate at really extreme operational scale, you can do things like this, sending off multiple hundreds of requests per individual user request to do lots of interesting things in parallel. And I'll give another example of this, which is the semi-magical Google ability to ask, did you really mean this when you typed in a search? The way that Google does that is when you issue a search against Google's ecosystem, you don't issue a single search, you issue several hundred. Because it takes your search string and permutates it in well-known misspelling ways, like transposing letters or substituting vowels and things like that. And if it comes back with a really high correlation for one of those and a really low for the rest of them, it'll come back and say, did you really mean this? Because I got really good search results back for this and almost nothing for that trash you typed in. So I think you probably meant this. And of course, they're right much of the time. But think about what that means from an operational standpoint. How many people are doing Google searches every second? And for each one of those, they're spinning off hundreds of service requests, and it's coming back almost instantaneously. That's a good example of being able to operate operationally at scale. Another common practice in this world is to embrace polyglot solutions. We don't really want to impose the same language or frameworks on every single team. Again, we're not trying to suggest that this becomes just total governance chaos here, but if you look at most large organizations and look at the spectrum of too many languages and platforms versus too few, most large companies fall well to the side of too few versus too many. And so from a microservices standpoint, you want to standardize on the gaps between services and be flexible in what happens inside the boxes. In other words, standardize on an integration architecture like REST Level 2 or REST Level 3, and let individual teams build right-sized technology choices for their individual services. You don't really care from an architectural standpoint because you're not coupled to anything they're building, and so there's no real compunction from an enterprise architecture standpoint to force them down a particular path, just from more from a sanity standpoint than a shared infrastructure standpoint. So Sam's advice, who wrote the microservices book, is have 1, 2, or maybe 3 ways of integrating and not 20, and pick some sensible conventions and stick with them. That becomes your integration architecture. When you talk about deployment in this world, you want to operationally make this simpler. So you don't want to make your operations have to understand all these different shapes of things that you're creating, a Ruby on Rails application, a Java application, a .NET application. You want to make those consistent, and so have a consistent deployment mechanism. This is why things like Docker are really, really popular right now, because Docker allows you to create what looks like to your operations group identical images of Linux or similar machines, but then you can run the individual kinds of things inside Docker containers, and so this is a very popular mechanism to do that for now. One of the interesting side effects of a services-based architecture is that it promotes coupling from application to integration architecture. So when you have a monolithic application architecture, you have a bunch of classes inside it, and they're collaborating with one another to do stuff. But when you start talking about a services-based system or microservices-based system, now those coupling points that used to be internal to your application architecture are part of your integration architecture. And there are a bunch of side effects of that. So one of these side effects is that you have to be a lot more explicit about coupling between these things in this world. Notice that each of these services still have internal coupling because they're still built. There may be a layered architecture inside there, some common kind of architectural patterns. But the way that these communicate with one another have to be a lot more coarse-grained now, and you have to think a lot more carefully about the volume and what kind of information passes along those links. We use things like consumer-driven contracts for safety nets, for engineering standpoint between these services so that we can evolve them more or less independently of one another. This coupling is much coarser grained than the coupling over here. Over here, you don't have to think much about, oh, well, I actually need to call this other method in this other class inside a loop and do it 1,000 times. That's no big deal. But over here, if you're doing that across your network, that's going to be hideously bad. If you're really undisciplined about your coupling, this can become a total mess. Your latency will become your enemy. This is the hazard of having a tool that generates service endpoints too easily for you. And coupling dynamics in this world become integration issues. So that becomes a much trickier thing to deal with. And in fact, let's talk about integration and disintegration in a services world. So here's where the practices of continuous delivery start interacting with operations and architecture. One of the really nice things that the Clojure community has given us, besides Clojure, is the guy who created Clojure, Rich Hickey, is also a word nut. And he's resurrected an archaic term that is perfect for software called complect, C-O-M-P-L-E-C-T. To complect things is to braid or weave them together. And very often problems in software is when we have inadvertently complected things together. And here's one of those places where mostly we have complected deployment and feature release. But in this world, there are a bunch of engineering practices that allow you to uncouple those things from one another. So in this world, components are deployed, meaning you move a component into a production ecosystem, but you haven't actually released the feature inside that component yet, because you can use things like feature toggles or feature flags. And so only after you've put that component live, made sure it's stable from a monitoring standpoint, then you can go in and release those features to the user. And in fact, this kind of ecosystem supports having maybe an almost identical version of that service. Maybe this is a different search algorithm or a different way of rating books or something like that. It still hasn't had an impact on your users yet, because in this world, applications consist of routing between these services. And so now you have a lot more flexibility. This makes something like continuous deployment a lot less scary, because what continuous deployment says is take all these components that have these new features and put them into production and monitor to make sure they're okay. But now I may want to turn on a handful of features at one time, and that constitutes a new release. I've continuously deployed all those components and know they're safe in my ecosystem, and I can turn on a group of features if I want to release it, so the users just think I've rolled out this new thing and all I've done is turned on these features. One of the things that we talk about in the continuous delivery world is this idea of blue-green deployments, where you have two identical versions of your infrastructure, a blue slice and a green slice, and you can move between those two slices of your infrastructure. Notice what we're talking about from a services standpoint here is really blue-green at the services level, because you can deploy something, release those features, route to it, and if it starts misbehaving, route back away from it, and you don't have to roll back your architecture or do anything draconian or drastic like that. Make changes, fix whatever the problem was, route to it again. Maybe just route 1% of your users to this new service and route the others to the old service, and do A/B testing to see if they like this new service better. All these architectures support all those kinds of behaviors. And so once you look at it from this perspective, as you get more and more services, you actually drive the risk of release down the larger number of services you have, as long as you have good engineering practices in place. Because if you're deploying a monolith, it's all risk. If you're doing a 2 a.m. on a Saturday morning deployment of a monolith, there's no mitigation of risk there. It's all or nothing. And the more services you have, you're displacing less and less stuff each time you put something live. We monitor heavily in this world. We monitor the services, but we also monitor the routes. And this is one of those innovations that Netflix came up with. They monitor routes, and any services that are no longer being called, they disintegrate out of their ecosystem. So they have a garbage collection architectural function that looks at services that no one's routing to anymore. That means that they've evolutionarily been passed by, and so they pull those out of their ecosystem. This requires a fair amount of engineering sophistication to do this, and so our mantra here is you must be at least this tall to use something like microservices. All these engineering practices pretty much have to be in place. These are much more complex architectures, but you get a much more interesting capabilities. The number one capability you get is that change becomes much less expensive because it's built in. If every component is self-contained, now change becomes really easy because you can move one self-contained component in and replace it, and very little fear of breaking things. That's the benefit. So from an evolutionary standpoint, when you think of decomposing a monolith into something like services, you need to find a way to partition things apart. And you'll find natural boundaries to do this with. So one of those are structural boundaries. I'll talk more about that in just a second. One may be domain boundaries. If you're starting a greenfield project, this is the inverse Conway maneuver. Separate things along domain boundaries and then build your system like that. But if you have an existing monolith, one of the trickiest things for you to untangle are going to be the transactional behaviors of that system. And so maybe that's the first partition you look for, is look for things that preserve existing transactional boundaries, and that becomes your first kind of service delineation, or the things that still don't break transactional boundaries. Those are easier to pull out of an existing monolith, and then maybe take that and break it into smaller and smaller services over time. You may do a structural exercise, and I talked a little bit about the structural exercise earlier. This is from an existing application that I did some work on, but you can definitely see structural hotspots in this code up in this corner and at the bottom on the left-hand side over there. Notice that by doing a little bit of an analysis from an X-ray standpoint, you can look and see how those things are coupled together and start thinking about, well, if all these are kind of related to one another and I don't have to cut as many red lines, then maybe structurally that's how I want to start pulling this thing apart. So to conclude, really what we're trying to support here from a continuous delivery and an architecture standpoint is architecture for change. Allow change to be a lot less expensive so that it can support the natural evolution of business a little more gracefully. Different parts of your business evolve at different rates, and we're trying to support and reify that in our architecture. I mentioned this idea of the inverse Conway maneuver, build teams that look like the architecture you want, and it will be easier to achieve that effect. I also mentioned efferent coupling as a code artifact, but you can also think a little more broadly about that and think of it as a team artifact as well. So if you're building services or microservices, don't make your whole team understand the entire world. They need to know about the things that they regularly collaborate and integrate with. They don't need to understand the entire universe. If they need to understand the whole universe, then you haven't done your partitioning of your services well. So this is kind of the whole thing together with deployment pipelines, et cetera. On a projector, you can actually see it. So you have small cross-functional inverse Conway teams with low efferent coupling deliver relatively independently into a common integration pipeline without fearing breaking each other's bills because they have consumer-driven contracts between them. They have an integration pipeline that is set up here to eagerly incorporate changes as quickly as possible and make sure it resolves diamond dependencies and those sorts of things so that these teams can work relatively independently with consumer-driven contracts for the things that they do need to know about and being blissfully unaware of the things they don't need to know about in the rest of the ecosystem and being able to produce changes with a good rate of speed and good cycle time without breaking stuff. It looks like I'm actually officially out of time, so I will go ahead and set you free now. If you have any questions, you can hang around a little bit after, and I'll be happy to answer them for you. And I'm doing an entire workshop on this subject on Friday as well. Thanks very much for coming. Hope you enjoyed it. Thanks. Properly doing continuous delivery. So you may have, for example, a commit stage and a functional testing stage and then user acceptance and staging and on and on. Each of these joined by a kind of a scratch area where you can keep things, intermediate results of builds as you build up more and more sophistication. Over time, the goal here is that you want increased confidence in production readiness. So you'll go through a more and more sophisticated battery of tests and those sort of things as you go along. In this continuous delivery world, pipeline stages become feedback opportunities. If you're accustomed to working an agile project now, you're accustomed to having continuous integration, and you started treating continuous integration kind of as a magic bucket where you can do a lot of stuff. So you build there and you run unit tests there, and maybe you do code coverage and other sorts of metrics and other things, and maybe you've got functional tests running and other things. What we're trying to encourage here is separate out that bucket of things, make them individual stages in a deployment pipeline, because that allows you to optimize the engineering practices around that stage and the audience for that stage, which is an important perspective. So you have to be the ones that set this up. But there's another responsibility that kind of comes along with this. There's a special stage in this deployment pipeline world where you start taking on additional responsibilities. In most of the continuous delivery literature, it's a user acceptance testing stage. That's just a coincidence of literature. You get to decide exactly when the stage is, but it's the stage in which you start really thinking about operationalizing what you're building. And so this is this idea of a deployment pipeline kind of spread out all together. The commit stage is what you normally think of as continuous integration. This is where your code is integrated and commit and unit tests and those sorts of things are run. This artifact repository is temporary storage on the file system to take intermediate artifacts that you've built and build up. All right, good morning, everyone. As you probably guessed, this is continuous delivery for architects. This is really the intersection of the engineering practices of continuous delivery with the role of architecture. And it turns out there are a lot of surprising amount of synergy between those two things, which I'm going to investigate as part of this talk. So I want to talk about three broad things in this talk. First, I want to talk about some related concepts around continuous delivery and architecture, including some engineering practices and some metrics and things like that. Then I'm going to talk about component-based development, both components, which are compile time dependencies, and services, which are runtime dependencies. This also touches on microservices, because that's just a specialized version of a service-based architecture. And then finally, how do you evolve from one kind of architecture to another, which seems a lot of people are doing these days. So let's first talk about some concepts in architecture. And the first one I need to talk about, of course, are some of the engineering practices in continuous delivery. From my perspective, continuous delivery really is just a convenient marketing umbrella term around efficient engineering practices for agile projects. And so continuous delivery has several parts. In fact, I'm doing an entire workshop on Friday about this subject, but a few of these things are particularly pertinent to architects. Now, one of those is this idea of a deployment pipeline. So in continuous delivery, you replace continuous integration with this idea of a deployment pipeline, which has multiple stages, and you try to achieve success through each of those stages, and you get more and more engineering sophistication in each one of those stages. And so as you look at a deployment pipeline, one of your first challenges as the architect is going to be exactly what stages do you have, because there's no prescribed set of stages that you are supposed to have before you're more and more sophistication. But you'll notice a particular step here under this acceptance testing stage called configure environment. And you'll notice that once you start doing that, you do that on all these downstream stages. This is the place in the continuous delivery world where you start spinning up the ecosystem that your code's going to run on. Because the perspective in continuous delivery is, look, your overarching goal is to make deployments a lot more predictable and stable. So how do you do that in a world where it has lots of moving parts and people keep adding more moving parts to it? The way you do that is start treating software as an entire universe, an entire ecosystem. So it's not just your source code, your database schemas, it's also the operating system that it runs on and all the ancillary stuff that makes it work. So this configure environment stage, so let's say you're building a Java web-based application. This configure environment stage, you'll now take a Puppet or Chef script and start from a raw IP address, almost always on a virtual machine now, and say, okay, this code needs to ultimately run on CentOS version something with Apache and Tomcat and 47 jar files and these user groups and permissions set up. So you'll spin up a Puppet or Chef script to build that environment up. You'll then deploy your binaries onto that environment, make sure that environment's up and running, and then run your acceptance tests on it, or do manual testing, but you still do that same configure environment stage. Even if you're doing continuous deployment, you're still doing that as part of that production push. You don't have to do that in this world, but that's the same kind of idea in this world. Now, whether it's a Puppet or Chef script or whether it's some sort of Docker image or something like that, the idea is, and the point of this is, that as the architect in this world, you have to start thinking about how does this work in operations much, much sooner than you have to in other kinds of architectures, which was kind of a last thing. Maybe you thought. What this really points out is that the abstract job of software architect is sometimes at odds with the practicalities of the messy real world. Because one of the goals of software architect very often is to achieve maximum code reuse. Try to build single sources of truth for things so that you don't have duplications running around all over the place. From a logical standpoint, that makes perfect sense because obviously duplication is bad. If you can unify things in a single place, that's a good design in an abstract way. But then you have to think about operationalizing this in a messy real world. Let me give you an example of where this ends up biting you. We have a client who runs an airline. And they, architects, had done as you would consider a best practice in the architecture world, built a customer service that encapsulates everything the organization knows about customers. It's all unified in one place. It's all backed by a clustered database that has the giant customer table and all of its ancillary join tables to it. So they've built a single source of truth for customer, which they're quite proud of. And then a volcano exploded in Iceland. And pretty much everyone who had tickets in this airline called their customer service desk to say, hey, is this volcano going off going to affect my airline ticket? Which means that people on the other side of the world couldn't board their airplane because now the customer service is completely slammed and it is now the single source of bottleneck. And because it is the only place you can go to get customer information, every part of the business is now affected. From a practical standpoint, this business would be much better off if they had two customer services, one that primarily dealt with boarding things and one that primarily dealt with customer service. And even if there was a little bit of duplication or, shocker of shockers, a little bit of conflicting information in those, about a little bit at the first of the project, and then the last of the project as you're getting ready to go live, you have to start thinking about it. Now this becomes a daily concern of the architect as what does this look like running in a production-like environment, because you're going to be managing this as part of the build cycle, as part of this deployment pipeline. What we'd ultimately like to get to, most of the literature in the continuous delivery world kind of assumes monolithic architectures, but the other goal that we're really after in that continuous delivery world is by doing smaller and smaller increments of change. So one of the engineering principles in the continuous delivery world is try to do things as eagerly as possible rather than putting them off as long as possible. And things like service packs or any kind of change to a component in our system, we want to try to incorporate that change as eagerly as we possibly can, because that is exactly the time when you pay the least engineering cost to incorporate something. The longer you wait to incorporate something, you pay a higher cost in terms of pain of getting that to work, because now you're letting combinations of things build up, which is the really tricky, complex thing in software. So where we really want to get in this world is have a system set up so that when one of the components changes in your world, in a compilation-based world, when one of your components changes, it automatically triggers a build that ultimately builds in an integration pipeline the application that you're building. And I'll talk about some of the challenges and other things with that in just a bit. Another kind of realization that this continuous delivery world, the way that this has changed the world of architecture, is it's starting to make us realize that yesterday's best practice is tomorrow's anti-pattern. We keep building architectures around constraints that exist, and then those constraints disappear, and the architecture with all those constraints built in exists for a long period of time.